Hello, welcome. Hello, welcome. Just going to wait a few minutes until 11, see who else comes on, and then we'll get started. Welcome, folks. Got another couple of minutes before we start the stream, but good to see a few of you in already. All right, I think we're going to get started. So welcome to the 13th day of remote learning. Today's joke is, what did the buffalo say when his son left? Bye, son. As always, reduce that like button to the lowest terms to show your support, and happy Wednesday. Today, we're going to go over instantaneous rate of change. Oh, sorry, I got some shake there. I'm going to go over instantaneous rate of change. We did this 4 or 5 days back, 7 days back, last Wednesday. And I had several people ask me some questions, and only one person handed in the answers. So that tells me that there was a lot of confusion about how to do this. It's very different from anything that we've ever done before. It's not particularly difficult. The process is very easy, but the idea is really confusing. And so I wanted to go over it and make sure that people understood it. There's a second reason that it's really important to go over this again, which is that this idea is the underlying idea for all of calculus. So whether you're going to do calculus at high school or whether you just need advanced functions as a prerequisite for post-secondary programs, but you will see some calculus concepts in post-secondary, this is going to be really helpful for you at both of those levels. So we're going to go over it today. And then you'll have a chance to go back and do the questions from day 9 and make sure that you're comfortable with instantaneous rate of change. This is such an important concept that usually in this course, we do instantaneous rate of change 5 or 6 different times. We do it once for polynomials, we do it again for rational functions, we do it again for exponential and logarithmic functions, we do it again for sine, cosine, tan, the trig functions. And then we do it again at the end for combined functions. So that's 5 different times that we see it. And that's because it's the fundamental idea for calculus. And so we want to make sure that people have a good understanding of it. So with all of that said, let's get started. I'm going to rotate the camera here, see if we can get it set up. And we're going to start with average rate of change. So pull that down, and let's get a focus. There we go. All right. And again, this is looking backwards to me on screen, so hopefully it's right side for you folks. But we are going to take a look at how to do average rate of change, and then we're going to talk about instantaneous rate of change because it comes from this. So this is going back to stuff you probably haven't touched on since grade 9. But we have a line, it has a slope, and the slope of the line is the rate of change of the relationship. So if we're looking at how fast does y change given a certain change in x, we're going to take the change in y divided by the change in x, and that is exactly the slope formula. So for this line, we have the point 1, 1, we have a second point 4, 3. And if we do the slope calculation, we're going to go y2 minus y1, or the change in y. And sometimes people will write this delta y. Those of you who've taken physics, you know delta means change. So this is the change in y. And in the denominator, we have x2 minus x1, and this is sometimes written delta x, or change in x. And then if we plug in the values, y2 is 3, y1 is 1, x2 is 4, x1 is 1, and we do the subtractions, we end up with a rate of change of 2/3. And so if here x was in hours and y was in kilometers, then this would be 2 kilometers per 3 hours. All right, so a very, very slow walk. So that's the idea of average rate of change. Just type 1 in the chat if you're feeling comfortable about that. Cool, thank you. All right, it looks like there's a pretty significant lag between when I'm saying things and when they're coming through for you. It took about 15 seconds between when I asked for the ones and when they showed up. So I'm going to try and keep that in mind as I go through. It may mean there's some longer pauses in the video, but that's just to make sure that when I ask a question that you have time to hear it and think it through and respond before I move on. So apologies if the pauses seem long after you've responded, but that's because of the lag. Okay, so we have this idea of rate of change, and we're going to take a look at one more average rate of change situation, and that is the situation if we have a parabola or any other nonlinear curve. So parabola, we'll just go y equals x squared, very simple one. So it goes through 0, 0, 1, 1, 2, 4, and it looks something like that, and of course continues out on this side as well. So the first thing to notice about this is that there's no single rate of change for the whole parabola. All right, if we look here, the amount of y is going up every time we go over on x. If we look here, the amount of y goes down every time we go to the right on x. So clearly here we have a positive rate of change. Clearly here we have a negative rate of change. They're not the same number. And in fact, just like slope, as it gets steeper, that means a higher slope and a higher rate of change. The same thing is true for a curve. So right here at the bottom, the steepness of the curve hits 0, the rate of change is 0. And then as we go up this other side, the rate of change is going to increase and get to higher and higher numbers. So we can't give one number for the rate of change for the entire parabola, but we can pick a section of the parabola and find the average rate of change. So in this case, the section I'm going to pick is from 0, 0 to 2, 4. So my starting point, P1, is going to be 0, 0. My ending point, P2, is going to be 2, 4. And we can find the average rate of change exactly the same way. Y2 minus Y1 over X2 minus X1. And that gives us 4 minus 0 over 2 minus 0. And it tells us that the average rate of change between x is 0 and x is 2 is going to be 2. And again, if this was in kilometers per hour, that would be 2 kilometers per hour. Or in other words, the average speed of a person whose distance follows this parabola relationship, their average speed over the first 2 hours would be 2 kilometers per hour. And if we looked at their average speed later on, it would be higher. If we went back this way and looked earlier, their average speed would be lower. But from 0 hours to 2 hours, their average speed was 2 kilometers an hour. Now, it's also important to recognize that doesn't mean that at any particular point in time, they were going at exactly 2 kilometers an hour. If we look at them here, their rate of speed is actually higher than 2 kilometers an hour. If we look at them down here, their rate of speed is actually lower than 2 kilometers an hour. It happens in this case, and this won't always be true, that the middle point is exactly where they hit the exact speed of 2 kilometers an hour. And we'll take a moment and show that later. So average rate of change, we're going to figure it out exactly this way. We can think of this as drawing the line through those 2 points. Draw a nice line through those 2 points and finding the slope of that line. Whenever we draw a line that cuts a curve in 2 places, we call that a secant line. So average rate of change for a curve is the slope of the secant line. And you might be wondering, hey, isn't secant that thing we saw in trigonometry? It's like 1 over cosine is secant. And yes, that is true. That is where the trigonometry secant gets its name. They're not exactly the same thing, but they're named the same because they come from the same idea. Kind of like when a ship sinks and when you have a kitchen sink, they're not at all the same thing, but they both come from the idea of things going away, right? When a ship sinks, it goes away. When things go down the drain in your kitchen sink, they go away. So they both get the name sink, but they're not the same thing. Secant line, same idea, not the same thing as a trigonometry secant, but there is some commonality to how they got their name. Okay, so curve is the slope of the secant line. That's our average rate of change. So the question for many hundreds of years, maybe even thousands of years, was, okay, if we have a line, we can find exact rate of change, and it's always the same. So at any instant on the line, we know what the rate of change is at that point. If we have a curve, we can find the average rate of change over a particular section of the curve. Both of those things are easy. But what if we want to know the exact rate of change at a specific point on the curve? Like, what if I want to know if this is my distance-time relationship and I'm at exactly 1 hour, how fast am I walking at that precise moment? Well, for a long time, people didn't have any ideas about how to do this. And then within a pretty short period of time, a few decades, 3 different mathematicians invented the same method, or essentially the same method. And the most famous of these mathematicians is Sir Isaac Newton, and the method is called calculus. So that is where calculus is going. We're going to talk today about just the very simplest idea, which is to use this slope formula to find instantaneous rate of change. So before we move into that, I'm going to give you a moment. If there's any questions you'd like to ask, you can type question in the chat and then type in your question. And I'll take about a 20-25 second break now and just see if you do have any questions so far. Okay, so looks like there are no questions. If you do have one and the lag has already interrupted you, please just go ahead and type it into the chat anyway. I will keep an eye out, and if I see one there, I'll pause what I'm saying and answer it. Okay, so how would we find instantaneous rate of change? Well, if we wanted to know the exact rate of change here, we could find what's called the tangent line. That is the line that just touches the curve at that point, and find its slope. The problem that we run into, because this idea was thought up a long time ago, the problem that we run into is, how do you find the slope of a line if you only know one point? Okay, so let's talk instantaneous rate of change. We'll add this to our notes. Instantaneous rate of change. And we know we want slope of the tangent line is instantaneous rate of change. Finding this slope is tricky because we only have one point. So if I tried to do the calculation right now, and I know I have the point 1, 1, I could say, okay, slope is going to be, well, just use the same point twice. So I'll go 1 minus 1 over 1 minus 1, and then I get 0 divided by 0. And of course, that doesn't give me anything useful And no matter what point I pick, it's always going to be something minus itself over something minus itself, and I'm going to end up with 0 over 0 every time. So not a very helpful calculation. So the bright idea that Newton had and Leibniz, oh, thank you, Caitlin. There we go. So if we only have one point, we're going to do that point minus itself divided by the x value minus itself, going to get 0 over 0. So the bright idea that Newton had was he said, well, instead of doing an exact point, I'll move this down, instead of finding the tangent line at this point, what if I take the secant line that goes from one side of the point to the other, and I just bring really close, like I move these points in and I get in super close here. Surely by picking two close points on either side of the point I want, I should be able to get a pretty good approximation. And the closer I move those points, the better the approximation I'm going to get. And so that seemed pretty reasonable. And you might be thinking, wow, that's calculus. Well, the next thing that Newton did is he said, how about I get those 2 points infinitely close to the point that I want? And he invented a technique for doing that. And that is what's called calculus. So we won't get into that today, but this general idea of just getting really close, we're going to do that. So in the Google Classroom, there's a document 3.02.h2 instantaneous rates of change for polynomials. And we're going to take a bit of time and go through a first example in there. And we're also going to fill in some of the blanks. So if you do have that printed out from a few days ago, you're welcome to follow along on there. So it says if we could create a line that touches the curve at only one point and is equidistant away from the rest of the curve, this line would be called a tangent. Tangent is the blank there to the curve. The very best estimate of the instantaneous rate of change at a point would be the slope of the tangent line. That's calculus. For now, the best we can do is the slope of a secant line over a very small interval around there. Okay, so I'm going to use the question that they have here, or to use the equation that they have here. So just make sure that I'm on screen. Yeah, there we go. Okay, oh, I'm seeing a comment from Daniela. I didn't get the last part. Could you show it for a few more seconds? For sure. So for this secant line, which cuts the curve in two places, we have 2 points from this line. We can pick that point on the curve and that point on the curve and take the line between them. So when we have those 2 points, it's easy to find the slope of the line, right? Slope formula uses 2 points and it works out great. When we want to get a tangent line, we only have 1 point. So the information I have about this tangent line isn't 2 points, it's just this single point, 1, 1. If I try and do my slope formula using only that single point, and I use it twice, so I go 1 minus 1 divided by 1 minus 1. In other words, y2 and y1 are the same value because it's just a single point. x2 and x1, I'm using the same point for both, so they're going to be the same value. Well, then I get 0 divided by 0, and we can't calculate that. And that's going to happen no matter what single point you pick. If you try to do the slope formula with both points being the same point, you're always going to end up with 0 over 0. And so that's not helpful. It doesn't let us calculate what we want. So hopefully that helps, Daniela. If there's a specific part you'd like me to talk a bit more about, let me know. And I'll try and keep an eye on the chat and get to that if I see a further question from you. Okay. So with that in mind, we're going to take a look at the equation from the handout called Instantaneous Rates of Change for Polynomials. I'll write it here. we're looking at thickness of ice over time. So T stands for the thickness, D stands for the day. And we have a cubic polynomial, negative 0.1 d cubed plus 1/3 d squared minus 4.4d plus 14.8. And we're talking about D being measured as number of days after December 31st. So January 1st is day 1, January 2nd is day 2, and so on. Okay. So we're going to skip ahead a little bit. We've already talked about average rate of change. So we're going to jump down to that larger empty section at the bottom of page 1 where it says calculate the average rate of change over the interval from 1 to 2 days. So average rate of change from D equals 1 to D equals 2. So the first thing that we need to do is we need to make ourselves a little table of values here so that we have the right 2 points to put in. So we have day 1, we have day 2. We can sub those into the equation. And so if I sub 1 into this equation, I'm going to get negative 0.1. 1 cubed is just 1, so plus 1.3. 1 squared is again 1, minus 4.4 times 1 is still 4.4, plus 14.8. And so we'll get that the ice was 11.6, I think it's centimeters. Yeah, thickness in centimeters, so 11.6 centimeters thick. So on day 1, the thickness of the ice is 11.6 centimeters. On day 2, we have negative 0.1 times 2 cubed. So we've subbed in 2 for the day, plus 1.3 times 2 squared. So I'm just going to make sure here. I think I forgot a times sign. Times, insert bracket. Okay, there we go. So 1.3 times 2 squared minus 4.4 times 2 plus 14.8, and we get 10.4 centimeters. So on January 2nd, on day 2, the thickness of the ice is 10.4 centimeters. So we want to know how fast was the ice thickness changing on average between January 1st and January 2nd. Well, we're just going to use our slope formula. Y2 is 10.4, Y1 is 11.6, X2 is 2, X1 is 1, and we can do this subtraction. We get negative 1.2 over 1, or negative 1.2 centimeters per day. So that's our average rate of change for the ice. Okay. Again, I'll pause, give you some time to ask questions there. That's an example of the average rate of change that we just talked about. Okay, so The next piece is instantaneous rate of change. And so if you go to the second page of the handout, you can see they're talking about centered intervals. And if you go down to the third page, you can see they're talking about difference quotient. That's two fancy names for two things that are almost exactly the same. We're only going to go through centered intervals. As you become familiar with centered intervals later on when you take calculus and they talk about difference quotient, it should be very familiar. And it's basically the same thing as centered intervals, except we move one of the endpoints a little bit. So instead of picking a point on either side, we pick a point on one side and then the point where we're trying to find the instantaneous rate of change. So they're basically the same process, just slightly different choice for the second point. Okay, so our goal here is to find the instantaneous rate of change from, or at, I should say, because we're at a particular point, at d equals 8. So exactly the moment where d equals 8, we don't know whether that's noon or whether that's midnight or what, but exactly that moment, we want to know how fast is the ice changing. So what we're going to do is say, okay, we need 2 points. If we just have 1 point, we're going to get 0 over 0. So we have to get 2 points. So the way that we're going to do that is we're going to choose d equals 7.5, a point slightly before it, and d equals 8.5, a point slightly after it. So we're just a little bit on each side here. And we're going to use those 2 points to, excuse me, we're going to use those 2 points to do our instantaneous rate of change calculation. So we again need our table, d for number of days, t of d for thickness of the ice, 7.5, 8.5. And I'm going to use Desmos for these calculations just because it'll speed things up. Here, f of x equals negative 0.1 d cubed plus 1.3 d squared minus 4.4 d plus 14.8. Okay. And so then if we do f of 7.5, we get 12.74 rounded to 2 decimal places. And if we do f of 8.5, we get 9.9125. And I guess I could not round them at all, which will make things better. So this is 77375. And so that's actually something I should make a point of. If you have, you should keep as many decimal places of accuracy as you can here. And the reason is the denominator in the rate of change is going to become really small as we pick points closer and closer to the one where we're trying to find the instantaneous rate of change. And when that denominator becomes really small, it's like multiplying the numerator by a really big number. And so even small differences in rounding can make a big difference in your end result. So we'll keep all the decimal places that we have for accuracy. Okay, so now I can just do the rate of change calculation. Y2 is 9.9125 minus Y1 is 12.7375 over X2 is 8.5 minus Y2 or X1 is 7.5. And so we'll do that calculation. 9.9125 minus 12.7375 equals negative 2.825 over 1. So in other words, our estimate is that on day 8, the ice thickness was dropping by 2.8 centimeters a day, or 2.825 centimeters a day. And so again, if you have questions in the chat, please just type them in. I'm not going to pause here, but I am going to keep an eye on the chat. And so if there's something you see that you're wondering about, let me know. Okay, so we picked 7.5 and 8.5 as points on either side of 8. And that gives us the instantaneous rate of change, or an estimate. So we should really say estimated instantaneous rate of change. At d equals 8 is negative 2.825 centimeters per day. And you can't see that, so I'll move it up. There we go. All right. So the question is, how good is this estimate? Well, 8.5 and 7.5 are close to 8, but we could definitely get a lot closer. And so you can see on the handout, they've got the same calculation for 7.9 and 8.1, which are closer. And then again for 7.99 and 8.01. And we're going to do that final one together as well. So if we make a table here, maybe I'll just add to this table 7.99, 8.01, and let me go over to Desmos where I've already got the polynomial in. So f of 7.99 is going to be 11.6278901. And notice I'm keeping every decimal place of accuracy that I have. And 8.01, we get 11.571889. Okay, so now we could choose those 2 points, d equals 7.99 and 8.01. They're closer to 8, so they should give us a better estimate for the instantaneous rate of change. So if we do that, we'll get m equals, well, y2, 11.571889 minus y1, 11.6278901 over x2, which is 8.01, or I guess d2, because it's d rather than x, minus 7.99. And if we evaluate that, try it out here, 11.571889 minus 11.6278901. So that's my numerator, and I'm going to divide it by 8.01 minus 7.99, and I'll get negative 2.80001. All right, and so therefore my new estimate, estimated instantaneous rate of change at d equals 8 is negative 2.8001 centimeters per day. And so you can see this is a little more accurate than the last one. We originally had negative 2.825. Now we have negative 2.80001. So I'm going to pause it there for some questions. Let me know what you're wondering. And we have a cat scratching at the door, so I've opened the door, which means we might get cat on video in a moment. Okay. Hello. We do have cat on video. Meow. All right, kitty. Time to come off the table. There we go. Okay. So as you can see, the process of finding an instantaneous rate of change isn't super complicated. We just pick values on either side of the point that we want. Typically, it's best to pick something that's like 1/100th away. So the ones we used here, that's going to give you a better estimate than being like half away, like 7.5 and 8.5. So pick two values that are really close on either side. You could even go 7.999 and 8.001. And that's going to give you a pretty good estimate of what's going on. And then you find the 2 points using the function. You just find the y value, and you put the 2 points into the slope formula, and that gives you the rate of change. And that is all there is to it. So over the next couple of days, if you can try out the questions that are in the handout 3.01 average rate of change, you can leave out part A, the average rate of change part, although you might find it useful to do a couple of them. But please hand in part B 1 through 6, which give you the average rate of or the instantaneous rate of change questions, and particularly questions 5 and 6 have that calculation for you to do. All right, so I'll stick around for a minute or two in case there are questions. And you feel free to ask about anything from today or from a few days ago. Because there's only 4 of you in the chat, if you wouldn't mind just leaving the stream open, and that way, even if we're down to just 1 student, we'll have a few more people in the chat so I can keep the stream going. I don't want to have to shut it down before everyone gets their questions answered. And if you're done and you don't have any questions, if you can just say goodbye or no questions or something like that in the chat. And so once I see that from all of you, then I'll shut the stream down. Do you resubmit the 3.02 sheet? If you have already submitted it, then no, you don't need to do this. Thanks, Daniela. But remember, I say if you haven't submitted it, if you could submit it and you can just put it in the current one in day 13, you don't have to go back and put it into day 9. Okay, sounds like everyone's good for questions. Thanks a lot, folks, and we'll see you on Friday.